time I presented just a basic introduction to intrinsic flat convergence. Today is going to be Ambrosio-Kirchheim's currents on metric spaces. So it won't have any of my results in today's talk at all. Let me just review the key aspects from the first lecture. In this world of intrinsic flat convergence, the class of spaces were integral current spaces. And they are metric spaces x dt. They have an integral current structure where xd is a metric space t is an integral current on the metric completion of x such that x itself is the set of t, and it wasn't always compact or complete. And the t encodes the orientation and weight on x. This includes manifolds. For a Riemannian manifold, the x would be the set of the Riemannian manifold, the d would be the distance taken by the infinite lengths of curves, and the t would be the notion of integrating over m, a differential form. In order to make this class of spaces rigorous, this is rigorously defined using Ambrosio-Kirchheim's notion of currents on metric spaces. That's what t is actually going to be. And so for today's talk, we're just going to focus on the work of Ambrosio and Kirchheim and make sure all of this is well defined, and also understand what properties Ambrosio and Kirchheim have already proven for these integral currents. So today's lesson, we're going to begin with a review of Federer-Fleming, which is in Annals 1960. The key ideas of Federer-Fleming have been put into a book by Federer called Geometric Measure Theory, which is about this fat. So I'm only going to give you a very brief review of this, okay? The main reason for that is for historical settings, just so you have a historical review. I'm not going to do anything detailed. The fact is Ambrosio-Kirchheim start completely from scratch, and so you can read their work without having ever read Federer-Fleming, and they have complete proofs of everything that they use, which do not in any way rely on Federer and Fleming. The Ambrosio-Kirchheim, so then we're going to do about basic ideas from Ambrosio-Kirchheim. Which is in what year? 2000. Note that these are I'll only discuss the theorems. I will not do any of their proofs. And they also have additional theorems, which I will not cover, including some work on the plateau problem. Okay, I won't be able to have time to discuss that at all. These work of Ambrosio-Kirchheim is building on work of DeGiorgi, multiple papers. And also prior work of Kirchheim. Concerning rectifiable spaces. But there's multiple works of DeGiorgi and Kirchheim, so I won't be able to provide those references. Now, it was just to give you some sense of where we're standing. In some sense, what I'm introducing you to today is a notion of the calculus that they're using. So this kind of matches Geely's talk. So let me just emphasize some points here. The world here, these x dt I mentioned last time, that such x dt are countably HM rectifiable. So they have Lipschitz charts. But you don't really like to use those charts so much. You just like to know that they exist. So a lot of the theory is based on T itself. Much of the theory, the properties, is not based on the charts. are based on T itself, on T, rather than the specific charts used to define it. Defined by T, or defining T. Obviously, there's multiple atlases that you could set up. So it would be an open, completely open question. What about integral current spaces satisfying CDKN or RCDKN? Are such spaces they should have a little more properties than just satisfying than ordinary CDKN. Now, you might say, what's the measure? There is a measure on these spaces with respect to the measure to mu equal the mass measure, which I will define today. So Ambrosio-Kirchheim defined a notion of a mass measure for currents. So that's a natural measure sitting on these spaces. We don't know much about them. We do know that if they are Riemannian manifolds and they satisfy Ricci bounded below, there's a lot of strong extra properties in terms of the flat convergence agreeing with the Gromov-Hausdorff. Okay, but it's unknown in general. All right. So here's the Federer-Fleming. So we take submanifolds. Phi, it goes from a manifold into a high-dimensional Euclidean space. So you have this Euclidean space, and you have your submanifold sitting inside it. All right, so we have this submanifold sitting inside high-dimensional Euclidean space, and we take omega is an n-dimensional differential form on En. Then you define it, you can be viewed as a current, which is written as T omega, which is also denoted like this. It's the submanifold. Oh, let me write it with a, sorry. My apologies. We have to push forward the manifold. Is the integral over M of the pullback of the form. So you pull back the form, you integrate it over M, so these need to be oriented in order to find this. Okay, a current is something which acts on a differential form. Once you have it defined this way, for example, you can take omega, omega is F d pi 1, wedge d pi 2, wedge d pi m. Then our T omega okay, so then we want to see what sorry, I've left out the omega here. Acting on omega. If omega is this, then phi number m omega is equal to integral over m. The pullback is f following phi, d pi 1 following phi, wedge d pi 2 following phi, wedge d pi m following phi. This is actually well defined even if phi is only Lipschitz. right? So that's a way of looking at a submanifold. So they were using this to study things like the plateau problem. They were wanting to understand if you're given a curve and you want to find the surface of smallest area bounding that curve. So it's a two-dimensional case, M is 2. They studied a sequence of submanifolds whose area was approaching the infimum, but they viewed them as currents and how they acted on differential forms, and then were able to study this by proving compactness theorems for such classes of currents. But then you need to know what is the larger space. So if you want to define convergence, just to be simple, weak convergence, you say Tj goes to T weakly if, so you can say Tj to T weakly as currents if Tj omega converges to T omega for all diff forms omega of compact support. In order to study this, Federer and Fleming had to define a notion, a larger class of notions that would include the limit spaces. So the limit spaces, limits of submanifolds that they were interested in were what's a notion called a rectifiable current, T. So a rectifiable current, T, is one that's not made out of a submanifold, but made out of accountable collections of Lipschitz images of charts. So T of omega is the sum from I equal 1 to infinity of some weight function here, theta I, integration over some AI of a pullback by some chart phi I of omega. And the AIs are in R of the correct dimension, M, or L. And the phi I's are Lipschitz to En. And the theta I's are integer. Now, they don't have to be integer, but let's make this integer rectifiable currents, then they are integer. Integer rectifiable currents, okay? So the theta I are integer valued. They could be constant, integer constants. Let's just make them constants. Some people say that they are integer valued Borel functions, but if I pull them out of the integral, then I have to make them constants, and the AIs have to be smaller. That's all. Okay, so that's our integer rectifiable current. And then once you have this integer rectifiable current, then you would want to define what's called the mass. So that's denoted M of T. And this mass, if these are disjoint, so let's just assume, just to make it simple, that will just be the sum from I equal 1 to infinity of the theta I's times the Hausdorff measure, M of phi I AI, if phi I AI, a pairwise disjoint. It's a little more complicated if they are not disjoint. If they're overlapping in a way of measure 0, it doesn't matter. If they're overlapping on top of each other in the same orientation, then just accumulates like this. But if they have the opposite orientation, there would be canceling going on. So that's this mass here. All right. Wow, I probably slid that way too far up, so someone will rescue me later, okay? Okay. All right, so in this setting here, we'll continue with Federer-Fleming. In this setting, you can define the boundary of a current. So the boundary of a current is equal to T d omega. So that's very natural. If it's a submanifold, that clearly comes out to be the boundary of the manifold. The push forward is T of the pullback. And that's well defined as long as phi is Lipschitz. You have the notion of an integral current. This is an integer rectifiable current whose boundary is also integer rectifiable. That is really impossible to determine by looking at these charts that are given here, because these AIs are just Borel sets. They can have absolutely horrific boundaries. So there is no reason whatsoever that you can take a boundary of the individual pieces of that sum. So in order to check if the boundary is also integer rectifiable, they actually prove a theorem, which is a really powerful and strong theorem that says if T is integer rectifiable and the mass of the boundary is finite, then T is integral. Okay, so there's ways of checking the mass of the boundary without actually having to figure out what the charts are for the boundary, right? So while I wrote the definition of mass here this way, that's just one way to find the mass, and there are a number of different ways to compute the mass by testing it against differential forms. So that's a very powerful theorem of Federer and Fleming that says you only need to check if the mass is finite. And then they have this definition of weak convergence, which I gave you up there, which just makes sense. And then they have a theorem that says, so we have their main theorem. The second main theorem is that if Ti are integral currents, and the mass of Ti plus the mass of the boundary Ti's are less than or equal to constant, less than infinity, then a subsequence converges weakly. This theorem is not proven by keeping track of charts in any way. What they do is they prove that there is this limit T, and it has all the properties of an integer rectifiable current, and that its boundary has all those properties. So the subsequence converges weakly, it says. Okay. Sorry there. So there's a subsequence that converges weakly. This is their famous compactness theorem. These are very difficult theorems to prove. All right? You're certainly not keeping track of the charts in any way. And then they define the flat distance. Yeah. It's integral, yeah. Yes, let me write this out in bigger words. Then a subsequence converges weakly to an integral current. And I forgot one thing. Sorry about this. I did forget. Very important fact. And the support of the TIs is in a compact set. Okay, So if the support, where they actually support it, is in a compact set, but the masses are uniformly bound, and the subsequence converges weakly to an integral current. And then there's the definition of the flat distance, which I gave last time, and they have a theorem that says that the flat convergence and weak convergence agree. Agree with these hypotheses. So just bear with me that I'm actually not going to talk about flat convergence at all today. So I'm really focusing on the currents and the weak convergence today. But I just making sure to have this theorem stated to you that at least in the Euclidean case, the two notions had been known to agree. Flat and weak convergence agree when you have the bounds on the mass and the restricted compact set. Okay. All right, so that's Federer and Fleming. Just want to make sure I said everything I wanted to say. Oh, one last very important property. That this weak convergence, so I'll put it here. It's very bad form, I know. If Ti converges to T weakly, then the limit as I goes to infinity of the mass of Ti's is greater than or equal to the mass of T. And this was crucial for studying the plateau problem. They're trying to find an infimum of volumes. The mass agrees with the volume when the submanifolds. They approach this, they get this limit, because when you're solving the plateau problem, you can guarantee these two things are controlled in C. You can cut off extra strands and make sure they're contained in a compact set. And so then you take the limit for the mass of Ti's. But Ti's are submanifolds, so that's just volumes or areas. You're going the areas down. And so that the mass of the limit guy is actually that infimum area. So you actually achieve the plateau problem for some integral current, which means at least it's rectifiable, and then you can call on people who are regularity experts to try to improve the regularity. In different dimensions, you get it regular, and other dimensions, you don't. Okay? So when it's regular or not will be progressed from that point. All right, so that's everything about Federer and Fleming. All right, so now we're going to switch to Ambrosio and Kirchheim. The first whole, they want to repeat this Federer-Fleming world. And in some sense, they achieve every single thing that Federer and Fleming have achieved, all right, with completely new proofs and extended. Of course, the problem is that there are no differential forms. So we want to define currents on metric spaces. Let's emphasize that they're complete metric spaces. So we need a notion to replace the notion of a differential form. And so they use the Georgi's idea. M plus 1 tuples, which consist of a function and m more functions. The first function is Lipschitz and bounded. Bounded and Lipschitz, that's what the little b is for. And the rest of the pi i's are just Lipschitz. And that's an m plus 1 tuple, and that's going to replace our differential form. So first thing we want to set up are some properties for these. So let's call this group dm plus 1. These guys, right? So we have these m plus 1 tuples are in the space dm plus 1. So we need to define some certain properties. So if we call this omega, tuple omega, okay, then we define d omega is equal to 1 f pi 1 to pi m. That satisfies the properties because 1 is a bounded Lipschitz function. F is still Lipschitz, so this is fine. Now, why is this defined as d omega? Well, let's look at that sample sample omega we gave up there, when it's a differential form of the form f d pi 1 wedge d pi m, that if you actually took d of that, that would be 1 df wedge d pi 1. So this is naturally matching the d operator acting on the specific example differential form up there. So not all differential forms can be turned into something like this, but at least that example can be. All right, so that's fine. That's the d. And the push forward, or the pullback, is f following phi, pi 1 following phi, to pi m following phi. And this is defined as long as is defined for phi Lipschitz from some z to w. Right?
Sorry,
yeah.
Is d squared 0?
No, it's not. And they're not alternating either. They're not alternating either. I'm not taking equivalence classes. I'm not taking equivalence classes, and my d squared is not 0. Very good interruption. Okay. I am not doing anything unless Ambrosio Kirchheim do it, and they do not put locality on their tuples, and neither does the Georgi. All right. All right, so this guy is fine. He pushes things around. And then we define a metric functional. So let me write warning. D squared not equal to 0, no alternating. All right. So we have a metric functional that's t is going to go from dk, this class of guys, I should make it a fancy d, m plus 1, to r. He has to be subadditive. So let's write down his two rules. T of x plus y has to be less than tx plus ty, and that t of t times x is less than or equal to t of x, where t is bigger than or equal to 0. Okay, so those are the two rules for our metric functional. Still not giving us any d squared equals 0 or anything. For such a guy, you can define the boundary t, who will be a new metric functional. The way he is defined on omega is to take t of d omega. So this is a new metric functional, boundary t. You get one metric functional t, you get boundary t. He goes from dm to r. Boundary t goes down one dimension. He still has those inequalities, not a problem. You can get the push forward. Number t omega is just t of the pullback of omega. That's fine. All checks, everything works using this pullback. And we get something called finite mass. This is a little more complicated. Okay, now we're going to leave the Georgi. This is 100% Ambrosio Kirchheim, the notion of finite mass. I'm pretty sure, anyway. Finite mass. So before defining mass, they define what it means to have finite mass. So they haven't defined mass for this t yet. They say it has finite mass if t acting on one of these tuples is less than or equal to the product from I equal 1 to infinity of the Lipschitz constants of the pi ice times the integral over z of f d mu for some mu finite in Borel on z. So that's what it means to have finite mass. You can find a measure mu that has this kind of behavior. All right? You'll notice that the mass defined by Ambrosio, by Federer-Fleming, that mass up there is finite if and only if it satisfies that on Euclidean space. So this does fit the old mass. So the old notion of mass in Euclidean space is finite under the same situations, if and only if. All right, so then what is the mass? Well, they define mass measure. The mass measure, T, is a measure. It's defined on any set A to equal mu of A, where mu is the smallest measure satisfying this. Okay, so yes, they spend pages to define what they mean by smallest measure and other properties about this, okay? But they have this mass measure. So that's what I mentioned before, that if you wanted to check if these have RCDK properties or what results, the natural measure to use on these spaces is this mass measure.
And this agrees in space.
With the mass measure there, which I didn't tell you about. Okay, yeah. All right. Well, so far, this is still really different from Euclidean space in some sense, because these omegas here are tuples. They're not alternating, and d squared is not zero, but we would like boundary squared t to be 0. Okay, so we need to add some more properties. All right, I need to be rescued. Somebody tall. Well, okay, tall compared to me, all right? Okay. All right, so we can leave this world of Federer-Fleming because we already saw the parallels. So I can certainly erase this. Let me leave that up a little longer. All right, everyone had time to think of questions?
Yeah, actually, we don't really care what they really want smallest measurement, right?
It's really complicated math.
Yeah, okay.
Luckily, they later get a formula for it. Right. When we get to integral currents, there's a nice formula. Okay.
Right.
But at the moment now, they need it to be finite mass. Now, the fact is that they restrict themselves to this world of finite mass very early in Ambrosio-Kirchheim. This makes a problem if you wanted to study manifolds which do not have finite volume. And so for that reason, Urs Lang and Stefan Wenger have a paper about something called local currents. Local currents is in the title somewhere. And in that paper, they avoid this finite mass condition on such a global scale and only require it on a local scale, and they develop a lot of theory there. But if not, all the theorems hold through, so you have to check over there what still carries over. But for now, we're actually going to impose finite mass as a very start of our definitions here. So let me just check one more thing. I wrote down finite mass. I told you the minimal measure. I told you the mass measure, and I didn't tell you the mass. Huh. Okay, the mass of T, this mass of T in their case, it just means the mass measure of the whole Z. Okay, so the mass of if you want to write M of T, it's actually mass measure, not an arbitrary set A, but the whole set Z, the biggest it could ever be. Right? Okay. Actually, I'll write that here. M of T is the mass measure of T acting on the whole space Z. Okay. And also a nice little estimate that the push forward of T mass measure is less than or equal to the Lipschitz constant of this phi to the power of the tuple. Remember, it's an m plus 1 tuple, so there's an m and an m plus 1, right? Dimension is m of phi, the push forward as a mass measure. Okay, so that's a useful inequality. So in particular, actually, you can show that if phi is distance preserving, you get equality. Yes? The pi's are the d pi i's, which is a little bit different from the dx i's. If you have a sample f d pi 1, wedge d pi 2, up to wedge d pi m, this replaces that. But don't presume that they're coordinate pi's, because that's a little too restrictive. That's what I mean. The f is the function in front. So I just erased it. Think of this guy as the parallel. But do not think of restricting it particularly to the coordinate ones. That's a little too restrictive. So just think of it as a bunch of bounded Lipschitz functions and sorry, Lipschitz functions and one bounded function, bounded Lipschitz function. So the d, right, d omega up there, right? D omega is 1 df wedge d pi 1 wedge d pi m, fits just right. And the pullback is exactly the same, okay? All right, this side of the board is still Federer-Fleming. I don't want you to, this side of the board is Ambrosio-Kirchheim. All right. We still haven't gotten it to the stage where we have this T that's actually a current that's sort of acting on forms. So now we're going to use the definition from Ambrosio-Kirchheim, definition AK of a current. T is a current if, and it's an M current, M-dimensional current, if it's multilinear in F pi 1 through pi k. So it's linear in each one of those terms separately, okay? If the limit as I goes to infinity of T F pi I1 pi I k. Notice the F is not allowed to change here. Okay, only the pi's are changing. Equals T F pi 1 through pi k if we're going to assume the pi ji's converge to pi j pointwise in Z with Lipschitz bounded uniformly. Okay, so if they have a uniform Lipschitz bound and they converge pointwise, then we require this condition, which is also true, somewhat in the other case. And then we have a locality principle, which is that T F pi 1 through pi k equals 0 if, I just want to make sure I say it exactly this way, there exists I such that pi I equals constant on a neighborhood of f equals 0. Now the reason I was looking at my notes so carefully is that although this is the definition, later they prove much better properties. Okay? So the definition is very few properties, and their goal is throughout to define things with as little properties as necessary so they can prove compactness theorems, but then consequences of having those properties will be tremendous. So although it's only this few properties here, soon they will have many more properties proven about them. Okay? So already from just this much, the properties that one obtains, so it's proven in a theorem, right, is that you get a product rule, you get a chain rule, you get a continuity allowing the f's to change, where the f's are allowed to change, and the f's only are required to converge in L1. In L1Z with the mass measure, though, used as the measure. And locality. That's better than this one, which I didn't write. Stronger locality. So you might say, what do you mean by a product rule? What do you mean by chain rule? So I should tell you what these rules are. So in the product rule, we can assume that we have an f and pi 1 are in lip bounded. I'm not going to write out the chain rule. It takes too long. But let me just write out the product rule just so you can get a feeling of it. T f pi 1 pi 2 through pi m is going to equal exactly what it should be if they were forms. Sorry, plus. Here. T pi f T pi 1 f pi 2 pi m equals, I should write it the opposite way. T1 f pi 1 pi 2 pi m. Okay, so let me explain this a little bit. I should have written this on the left, but I'm just using Ambrose. this is like saying, what is d f pi 1? It's df pi 1 plus f d pi 1. So that's why it's f d pi 1 df. Okay, so this is proven not on the scale of the tuple, but on the scale of the t acting on the tuple. So the tuples are not given the properties of differential forms, but the way t's act on them give them those properties. Right? The chain rule is kind of a messy one, but maybe it is worth writing down, just so you get a good feeling for this thing. So there's a continuity and there's a stronger locality. I'm just going to erase these two so I can write the chain rule out. It needs more space. So the chain rule, if I write it out, says that t of f psi following pi 1, psi following pi k. So think of this as you're going to have the determinant of the Jacobian appearing here, right? Because this is d of this guy wedged with d of that. So there should be some sort of Jacobian appearing. And sure enough, you do have that. It's t of f, determinant grad psi, pi 1 through pi k, if psi is C1 from R, K to RK, or RM to RM. This is an M. Okay, so they need C1 to get this. I'm sure you could do it with weaker. They don't care. Okay, one of the results of this is suppose that all psi does is reorder the indices. Right? It just says, oh, I'm going to take psi as just a permutation of the indices. As a consequence of the chain rule, we get finally the property of forms, which is that pi 1, if I permute the indices sigma 1 dot 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 pi sigma m, this equals negative 1 to the sine sigma, or sine sigma t f pi 1 pi m. So we finally get that property of differential forms, but only inside the current t. So I put this board where you can see everything. That's only a couple pages, actually. These are not nearly as bad as the later stuff. Yeah. Yeah, but they get it as a consequence of the whole chain rule, because they need the chain rule anyway. Yeah, yeah. So, so it's effectively a consequence of 3 and 1. So yeah, this proof is in the beginning of the paper, very well written, very clear, very easy to follow through here. The really difficult parts come when they're trying to prove these compactness theorems, and that a mass of a boundary being finite is enough to get it to be an integral current. These are very serious, difficult theorems. But this beginning part is fun and easy. Okay, it's nice to read. Just so long as you get past the idea that the tuples were already supposed to have been formed. The whole paper is much easier to read than Federer. Okay, so trying to follow their compactness theorem is much, much more difficult. All right, I suppose I should squeegee it, right? Squeegee side. Yeah, that's true. And you can actually use Ambrosio-Kirchheim's proof as a third new proof of the Euclidean case, too. So in Francois Lin's geometric measure theory book, he proves the Federer-Fleming compactness theorem using the Ambrosio-Kirchheim approach because he thinks it's more elegant. So, okay. All right, so we've got all of that. All right, so now I need to go over what properties. Finite mass measure. All right, so let's look at these properties from Federer-Fleming and ask which ones of them are still holding, right? So we do have the boundary. That's fine. The push forward is fine. Now we want to define integral current. So we want a notion of integer rectifiable current, not just current. So far we've only got current, right? So definition T, this is a Cambridge-Kirchhoff definition. T is an integer rectifiable current actually, I'm going to be fair. They made a mess if, and they give a very complicated thing. Blah, 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 blah. All right? But they have a theorem. That's easier to follow. Okay? T is an integer rectifiable current. Remember, it's a very simple statement that's easy to prove, but actually complicated to state. Okay. Integer rectifiable if there exists phi i's from ai's to z. The ai's are, these are by Lipschitz, and the ai's are sitting in Rm and are Borel. And there are theta i's, which are on ai to z, that are integer valued, which it says right there, and they're Borel, are Borel measurable, such that T acting on f pi 1 through pi m, that's what we'll have to define, right? T acting on f pi 1 through pi m is equal to the sum I equal 1 to infinity. There are countably many of these theta i's, integral over ai's of the f. Oh, no, let me just. These are the phi i's. These are like our charts. F following phi I. F is a function on z, right? Okay. D pi 1 following phi I. Wedge. D pi m following phi I. This is all well defined as long as the phi i's are by Lipschitz, so that's fine. The f was bounded Lipschitz, so this is a nice differential form here. Okay, so this is a nice differential form defined almost everywhere. Okay, so that's a theorem in their case. The actual definition of integer rectifiable current involves saying that the set of the current is rectifiable and that there's some sort of integer weighting going on in a more complicated way. But this is the theorem that says what they are. Let me just point out that this.
Sorry, what is that integral with respect to? So this is with respect to the Hausdorff measure?
No, this is on AI inside RM.
Oh.
Yeah. So this is a classic form integration. And it's almost everywhere Lebesgue, M. LM almost everywhere. That's a good question. So that's pretty much exactly the same as Federer-Fleming's. Okay? Now the mass had that different definition. Do we still have the mass measure here? The Federer-Fleming definition of mass was the sum of these theta i's and Hausdorff measures of the ai's. And the mass measure here has already been defined in a different way. And so when they actually try to compute what is the mass measure when it has this form, it actually comes out to be different. So it doesn't quite line up with the Euclidean one. And the way in which it's different is we need to, in this case, so there's a theorem. And this is a huge, difficult theorem, okay? That the mass measure that's been defined right here as the smallest measure satisfying star, in the case when it's an integral current, turns out to be theta lambda Hausdorff measure of dimension m restricted to the set of t, where set of t, I defined last time, but I'll write it again, is the x's such that the lim inf as r goes to 0 of the mass measure of a ball of radius r over r to the m is positive. So you have this set of positive density for the mass, for the current, which means you test the mass measure on a ball of radius r divided by r to the m. M is the dimension that we're talking about. That has to be positive. So it's a major theorem of Ambrosio-Kirchheim that this mass measure has this form, where it's the theta, the function. This is sort of like an infinitesimal definition. It's a little vague what exactly they're meaning here. I guess you should really say that the d of t over this Hausdorff measure comes out to be theta lambda, because theta is a function and lambda is a function. All right? Think of theta as a function and lambda as a function. This lambda is the crucial difference. In Federer-Fleming, there would be no lambda. So what is this lambda? This lambda is actually called it's an area factor. Lambda is equal to 2 to the k, 2 to the m over omega m. That's the volume in a Euclidean space of a ball of dimension m, sup of the Hausdorff measure of a ball of radius 1 over the Hausdorff measure of a ball of radius r. So this is a parallel pipette, such that r is a parallel pipette, containing B1. Okay, this is really hard to read. Okay, so I have to explain that. At x, we're talking about this being a parallelepiped in the approximate tangent plane to set t. All right, so what does that mean? So you have this set of t, which is this set. And now you take the t, or you don't even have to say set t, you could just say t. If you want to understand what the approximate tangent plane is, you scale out the t. So you take your fix your point x and your t, and you scale out. You take the weak limit. So this gives you an approximate tangent plane. Existence and stuff is a theorem. It's a big deal. It's not easy, all right? So once you've got this tangent plane, then this question of whether this is Hilbert or not comes up. This is all because of the Finsler effect going on here, all right? So if it's Hilbert, then the parallelepiped containing the ball of that metric exactly is the cube, whose volume is 2 to the m, so this comes out to be 1. So if the tangent plane is nice Hilbert, ordinary Euclidean plane, then you have lambda x is 1. And you get the exact same formula as Federer-Fleming has. However, if the unit ball is a square, like in Jiggly's talk, then you have to find the parallelepiped that contains that ball, which is the square itself. And so then you get this factor coming out in front. Okay, so if it's exactly the standard square, the ball and the small parallelepiped containing it are exactly the same thing, and then you get this factor appearing everywhere. If it's the diamond, then the parallelepiped is off. So then it gets a worse error. And in fact, they have a bound. This is called an area factor. It's been studied by other people, and this area factor is bounded. There are controls on it depending on dimension. These are all dead. Okay, wet chalk does not work. It's called the area factor. Okay, so we have this area factor coming up. This area factor depends on every point. Some of the tangent planes might be Euclidean. Other ones could be other norms on Euclidean space. All of them will be Euclidean space at dimension m, but they will have different norms on them. So this is depending on the norm on the tangent space. All right, so that's the a distinction. So let's, yeah. I should say it's C+, yeah. Sorry, thank you for saying that. Just change the orientation on the AIs if you wanted to allow a negative theta. But yeah, you want it to be positive at this point. So, thanks for that, yeah. I put them positive in the other one, right? In the Federer-Fleming. It's already erased. Okay. All right, so we have boundaries are fine, push forwards are fine, integral currents and integer rectifiable current whose boundaries also integer rectifiable. That definition is the same. Actually, let me slide this up so I can mark which ones are the same. And now I need someone of moderate height. If you refuse to be called tall. All right. We'll just erase the Federer-Fleming here. They don't want to be erased. Ambrosio-Kirchheim. This is the same, that's the same. An integral current is an integer rectifiable current whose boundary is also integer rectifiable. That's the same definition. Theorem, if T is integer rectifiable and the mass of the boundary T is finite, then T is integral. 10, 15 pages of the paper. Okay, very, very difficult theorem. Just getting from the mass is finite to having the charts. Compactness theorem, if TIs are integral currents and the mass of TI, the mass of boundary TI is less than or equal to C, and the support of T is contained in a compact K, or if Z itself is compact, for example, then a subsequence converges weakly to an integral current. Same definition of weak convergence. And the flat and weak, this is not Ambrosio-Kirchheim. Wenger has a paper where he proves this one. It's called flat convergence of currents, okay? But all of these are Ambrosio-Kirchheim. They recover every one of these results. How much time do I have? Oh, perfect. I finished, right? Yes. I finished, and I'm done. That's it. Okay. This theorem is another 20 pages. The proof of this theorem involves something called slicing. For those of you who know geometric measure theory, there's a slicing theorem. They both have the same theorem. Okay? And they have the proof is using slicing. They slice it down until they get to zero-dimensional, and they do zero-dimensional by hand. And then they build it back up. I thank you very much. Yes. Yeah, you would want to show that if it's RCD, the lambda is 1. It's got to be. But I mean, I haven't proven it at all. But I mean, intuitively, it has to be. Yeah.
Can we also define variables on the
No. No, not that I know of. Has anyone defined varifolds on metric spaces?
I mean, they don't do it.
Absolutely not. So the varifolds on Euclidean spaces require the tangent space to the Euclidean spaces. Yeah. So they're measures on well, equivalent to having, they're measures on tangent spaces. Yeah, yeah. So. Just to make one point, in terms of those of you who do know about Gromov filling volumes, the fact that the mass is defined this way is one reason it's not exactly the same definition as Gromov's filling volumes. Gromov's filling volumes involve chains, and he has different kind of area factors. And Barago and Ivanov also study spaces, and they use different area factors. This area factor is all set up so that that mass is the infimum of those measures, which ends up being very important, that this is the definition of mass later to do their work. And then that ended up giving this one, but it didn't agree with prior notions of volumes, square volumes, things like this. And just to emphasize, it's not listed here. Oh, here it is. This one is also AK. Very important. Weak convergence gives a limit for the masses is bigger than the masses. This is also in Ambrosio-Kirchheim. Okay, thanks.